All right, getting ready. Yeah, so what is it? Um, so I hope you all enjoyed the talks of Mark Chaplin last week. I thought they were absolutely awesome. And we kind of continue in this vein. So I'm essentially done with how should I say, the teaching bits. And so now we're really entering into active research. And what I'd like you to present today is also active research. I think it's a very hot topic. Talking about glioma and how glioma invades into healthy tissue. So I'll show you later, a little bit later, I'll show you videos about glioma cells invading tissues, and I hope you will be excited or amazed. Yeah, amazed is the right word. Amazing. So, but not only this. So this is a presentation I also gave yesterday here at the Fields Institute. But in this class now, I will fill in many of the details which I had to leave out at the talk. So this is then still also teaching. So it's a mixture of research, presentation, and also teaching of interesting methods. I don't know if you ever thought about glioma so much. Let me show you here images of glioma. So these are brain tumors, which are imaged with MRI scans, and you see these whitish regions, right? I think I can draw on them. So these whitish regions here, these are tumors. And in these images, it is really, really difficult to delineate the boundaries. So if you try maybe on this one to kind of draw a line, what the tumor is and what not, it is very diffuse. So it is not easy to draw this line. And maybe even if I do it, or if a clinician does it, or if a different clinician does it, they might draw different lines altogether. Okay, just a second. So these tumors have very diffuse nature. Hi, Sumera, how are you? So I'm getting my first customer in the room today. The others are sitting in the other talk, so that's fine. So very diffuse. In particular, here on this one, it would be very difficult to delineate the boundary. And so a characterization of these glioma, which are the most serious brain tumors, is a very diffuse invasion. Diffuse. So then, which makes sense to look for diffusion equations, right? And we learned a lot about reaction diffusion equations. Also, Mark Chaplin has been using those. So it makes sense as a first idea maybe to use kind of a diffusion or reaction diffusion equation to try to model this. And this has been done, for example, here in the proliferation infiltration model by Christine Swanson. So Christine Swanson is currently at the Mayo Cancer Center in, I think, Arizona. And she is definitely the leading expert who was one of the first modeling glioma. And she used a model of this type. Let me write it down. So du by dt. We have u of x and t to be the cancer cell density. And then we use a diffusion equation, d of x Laplace u, plus a logistic term, mu u1 minus u. So the logistic term we have seen many times, so there's no mystery here. This is a diffusion term. The Laplacian, right? You remember Laplacian, I just maybe remind you, d square by dx1 square of u plus d square by dx2 square of u, and so on. Dxn square of u. That's the Laplacian. And the d of x in this model is split into two components. Let's call this 1 and 5. They assume it is 5 times higher in white matter. And it is 1 in gray matter. So what is this? Well, the brain essentially can be divided into two tissue types, white matter and gray matter. Gray matter is where the brain function happens, where all the brain cells are, and the brain function happens, whereas white matter is the connecting fibers, the connecting nerve fibers. So then nerve fibers could be connecting different hemispheres, so it's like this, or they connect different parts of the brain. I should have gotten pictures of this, but anyways. So white matters are the nerve fibers. Gray matter is the substance of the brain where the thinking happens. And the assumed diffusion in white matter tissue is 5 times as high as in the gray matter. Important here is the typical Fisher KPP structure, right? This is a Fisher KPP model, a diffusion term, a logistic term. And we have seen this in Mark Chaplin's talks as well. So now this model is famous, has been used by many people, by Russ Rockne, by Hawkins Darude, by John Löwengroup, and by many, many more. There are more than 200 papers on this model. There's another model, which is the go or grow model, or go or grow models. They came around about 2012. And here the idea is that you have 2 cell compartments. One cell type is moving, and the other cell type is reproducing, but they don't do it at the same time. And so then we have a moving compartment, and we have a proliferating or dividing compartment. They call them U and V. So then we have du by dt. So this is moving, so we do a diffusion term here. And dv by dt, this is reproducing, mu v 1 minus v, not moving. And then we have transitions between those. So we have minus alpha u here, and they go here. Alpha plus alpha u, and then we have they're leaving this compartment minus beta v, and then plus beta v here. So the alpha and beta are the transition rates between these compartments, and in the top compartment is only moving, and in the bottom compartment is only cell division, reproducing. So the structure is kind of similar, right? It has both processes as the Swanson model as well. The d of x, of course, you can do the d of x here as well, using the same diffusion coefficient. So these are go or grow models, and they have been used for glioma as well. And then there's a third class, which are anisotropic diffusion models, and I have been involved in the derivation of those. And these are the following form: du by dt is nabla colon, and then comes the diffusion tensor d of x u plus mu u 1 minus u. Okay, so what is changing here is the diffusion term all of a sudden becomes much more complicated. And I should tell you a little bit more about this. So insert a page, annotate, and my pen is too large. So what does this nabla colon d of x mean? So this d with a double line is a tensor, so it's a matrix, d11 of x, and d12 of x, and so on, d1n of x, dn1 of x to dnn of x. Okay, so it is a full n-dimensional matrix where n is our space dimension, and the entries are dij. So often I would just write it as dij ij. And now the second derivative is all second derivative combinations you can possibly make. So nabla colon d of x u is then the sum over all I and j is 1 to n, d by dxi, d by dxj, and then dij of x u. And that's it. Okay. Right, so you build all top possible second derivatives you can with the coefficients dij of x. Special case.
Can I ask?
Yes.
Sorry.
Yes.
Why are we calling it a tensor and not just a matrix?
Yeah, we can call it a matrix as well.
Okay. Is
Yeah.
it like, is there like a more general version that it would be a tensor and not a matrix, or?
Um, right. It is called a tensor because later we will inform the values of these D11, D12 from medical imaging. And this imaging we are using is called diffusion tensor imaging. And I think the word tensor comes from there. So there's a modality that's called diffusion tensor imaging, which gives us an idea how to measure this matrix. Yeah.
Okay, okay.
Imaging. And you know, in two yeah, as a map on two vectors, they can be identified, right? A matrix is the same as a two tensor. Yeah.
Mm-hmm. Yeah.
Yeah. DTI. So let's look at a special case, and the special case is just a diagonal matrix which has, let's say, only ones in the diagonal. No, let's make it a D. That has a little D in the diagonal. Otherwise, it is entirely zero. Okay, if you sub this into our colon formula here, into nabla nabla colon d of x. So what do you get? Well, then the sum is only over the diagonal elements. So you get d by dxi, d by dxi. And the diffusion coefficient is only the same d always, which you can factor out. And so then if you write this all out, you get just d Laplace u. So then in this sense, the anisotropic derivative is a generalization of the Laplacian, because for a special matrix or for a special tensor, you get the Laplacian right here. So this is happening in the anisotropic case. Okay. So yeah, let's go back. So here we have an anisotropic diffusion term. Here we have split it up between a diffusing compartment and a growing compartment. And here, this is the simplest case. We have them together in the isotropic form. And all this is based on the idea that the tumor should diffuse, that this is very diffusive invasive. What we didn't know at those times, so this goes back to 2012, 2008, and so on, we actually didn't know how the cancer cells really move. And only about 2015 or so, there was a fundamental paper by Oswald where they were able to show how cancer cells actually move in tissue. And then we can ask ourselves, is our model assumptions actually correct or not? And so here's a picture from the Oswald paper. I'll show you videos in a second, but first I want to explain this. So what happens here is extension of tumor microtubes. Microtubes, which are these thin protrusions. So you see in green are the cancer cells, red are the blood vessels. And the cancer is growing from the top to the bottom here. It is invading to the bottom. And you see the cancer cells, they send out very thin protrusions, these green extensions here, which are called the tumor microtubes. So maybe I should give this an arrow here. So here is one, here is one, right? You see them very clearly. And the thicker ones, which look like beans, these are the cancer cells. So that use these microtubes to invade, and then they also form a network. So further into the tumor here, there will be a network of cells connected by these microtubes. So in this microscopic picture, it does actually not look like a diffusion process. It looks like a guided movement along these microtube networks. I should also say this is experiments done in living mice. So somehow they are able to keep mice alive and look at their brain tissue while the tumor grows. It's completely crazy. So let me show you the videos. Here is the first one where we see this process in action if the link works. Why does it not work now? That's strange. No? Yes. So here's the video of the still image I just shown you. So you will see from top in green, the glioma cells invading. They extend microtubes, and then they grow from the microtubes, and then they send new microtubes and grow, and they form a network. And then this is how the tumor looks. Maybe I should show this again. It was so quick. And I hope that's okay on the Zoom. Yeah, I think it is okay. And then in the second half of this video, they focus on two microtubes. One is extending and one is retracting in the box. Just look in the box. There are two of these lines. One goes back and one goes further. So maybe I show this again also. So maybe from here. And they're pretty straight and they're pretty long and they can extend or they can retract. Okay. So then the second video I want to show is a Z-stack. So now they take a fully grown tumor and they go level by level from top to bottom through the tumor. And you see the tumor cells in green and the connecting network from these microtubes, which has formed. So this is now the established tumor. You also see the blood vessels as we go through, and you see the connection. So they form a tight connection of this. And then, well, being kind of brain cells, so then what they do from this connection, they communicate. So they can send calcium signaling through this network. So here you see lighting up tumor cells. These are tumor cells again. They're connected and they're firing. They're firing signals. And this is totally crazy, right? A tumor shouldn't do this. This is, like a galaxy of tumors. Yeah, yeah, it does. That's why. So here we go. So they participate in calcium signaling. So this is what a healthy brain should do, right? In a brain, you release chemical potentials and connections through your nerve cells, but a tumor shouldn't do this. So it's a little bit like a thinking tumor, as if it were thinking. So very scary and also very cool to observe. Okay. So this is the process we are interested in. Yep.
Why are you suggesting that tumors should not do this? Like, I mean, cancer cells are cells that lost some of their functions, but I mean, I expect them to do some functions that normal tissues do, and signaling is one of them, right?
Fantastic. Oh, this is a very good comment. Thank you. Yeah. So from this point of view, you might be right. Yeah. I was surprised. I thought glioma cells are kind of damaged and they can't do anything but just grow. But you're right. It makes sense to assume they preserve some of their function. Yeah. Good comment. Thank you. So then what I like to do in this little presentation here is talk first about the modeling of tumor microtube-driven invasion, then talk about scaling limits and make relations back to the existing models, which I mentioned earlier. I have a result on traveling waves, which is a little bit more mathematical. And then I talk about a wound healing assay, which is work Alexandra did, and she just came into the room. And then I talked about applications to glioma patients. So how far are we in the modeling and where is this used? Okay. So here are some facts about the microtubes. So they arise in 93% of astrocytomas. Astrocytomas is a special kind of glioblastoma. And so they are very prevalent in astrocytomas, and less so in oligodendrogliomas. The tips extend and can also retract. We saw this. They follow directional features of the brain, such as blood vessels or nerve fibers. Glioma nuclei divide separately, and then they are transported along these tumor microtubes. And then they settle somewhere and they form new tumor bulk cells. And then a glioma tumor microtube network forms and communication via calcium waves then is possible. Okay. So there is a paper, a recent paper by Martina Conte in 2022, where she looked at the detailed biochemical modeling of the microtube extension. But our approach is a little bit different. Did I lose my microphone? Okay. because we we are interested in the spatial spread of these tumors. So after long discussions with my collaborators, which is Ryan Thiessen, Nadia Loy, and Kevin Painter, we came up with a model which has 5 ingredients. So which has a tumor microtube tips, which are here indicated in red. They lead the invasion, and then they lay down the tumor microtubes, which I call M. And behind the microtubes come the bulk cells, which I call B. And on the microtubes, for example, here we have moving nuclei, which I call N, and then the moving nuclei, the rest, and then the resting nuclei form new cells or new cancer cells. So, so we started with these 5 ingredients for a model. Now, you see some of them depend on a V and others don't. So T is time, X is space, and V is a direction, because the tips invade into a certain direction, right? This is not just a random walk. They follow maybe white matter fibers, or they follow a blood vessel. So we have directed movement of these tips. We have directed movement or directed growth of the microtubes. They have a direction. And then the moving nuclei, they move along the microtubes, so they are also parameterized with a direction. And so what we get is a coupled system of variables that depend on V and variables that do not, like B and R. They have no more direction. So this looks already complicated. And then for the tips and for the moving nuclei, we use transport equation framework. And I show you the first equation here. And at the start, it looks a bit scary, but I will carefully introduce these terms. So this is for the tips. So then this here, this describes transport of the tips in direction V. V is the direction, and SP is the speed. How quickly they grow. And this is the direction. And that's the direction they take. So if the right-hand side would be 0, then this is just uniform movement in direction V. But they change direction, and this is this term, which is described by an integral operator L. And I will show you a little bit about the integral operator in a second. But let's first talk about the other terms. So then we have a decay term, so we can lose tips. We have an anastomosis term. When a tip meets a tumor cell, then they form a connection. And then we have the production of new tips, which come from bulk cells, using like a logistic term for the production of new tips. The model is kind of based on an idea by Leah Keshet on fungal growth, describing how fungus grows. Yeah. So let me talk about this integral operator thing a little bit. Now insert a page. Okay. So yeah, let's write this out. So we have PT plus SPV times gradient P. So that's the left-hand side. I didn't change anything, but now I write down the integral term. So minus mu P plus mu integral over V, T of V, V prime, P of Tx, V prime, dV prime. So this is everything which is in this LP. So what is this? So mu here is a turning rate. So this describes how often the microtube tips change the direction. And from the images, they do not change the direction very often. So mu is small, but they do. They can adjust the direction just a little bit. So mu is the turning rate, and then T of VV prime. This tells you if a tip has a previous direction V prime, what is the probability to choose a new direction V? So that's the probability or probability density to switch from V prime to V. So T of VV prime is the probability density of switching from V prime to V. Okay? And all this together, I call this integral operator L of P, just to have the writing a bit easier. One important example is a Pearson walk, and let me introduce this right away. I will work with the Pearson walk in a second as well. So Pearson walk is the walk where you have no bias. You have no preferred direction. If you switch, you just choose anything at random, just anything. And in this case, t becomes a constant, okay? Pearson walk would then be a t of v prime is a constant, and the constant is 1 over the size of the velocity space, v. Okay, so the big V is all possible velocities. Okay, I do an example of this too. Example, V could be like the speed times Sn minus 1, where now Sn minus 1 is a unit sphere. So let's plot this in 3D. Then we have a sphere or a ball. Okay, and the radius is Sp. And so you have a ball of radius Sp. And for a ball of radius Sp, you know a formula for the surface area. And so then this would be the formula here. Okay, what is the radius? What is the surface area of a sphere? Who knows? Something is blocking? Oh, what is this? Software update. Update now. Okay. But I can move it over, I guess I can, or at least make it smaller, yeah. Now we can see it. Who knows the formula for the area of a sphere? 4/3 pi r square or something? Come on, somebody needs to know that. There it is. 4 pi, is it 4 pi square? No, 4 pi r square. Yeah. So then V would be, thank you very much, 4 pi, and then SP squared. Okay, so depending on the case, we can compute this size of V, and we know what it is. But now let's put it into our transport equation, this Pearson walk. So then we get PT plus SPV gradient P equals minus mu P plus mu. Okay, now the T is a constant, so I can just take it out of the integration, size of V. And then we just need to integrate the P Tx V prime dV prime, and now I'm running out of space. Dv prime. And so the equation simplifies a little bit. Now we just have to deal with an integral and no longer with a kernel inside. So I come back to this and I make it a little bit bigger in a second. Okay, so this is the movement of the tips. Now the tips lay down the tumor microtubes, which happens here. And then the microtubes can mature if a nucleus comes into them, into bulk cells. So that is this term. And then the bulk can grow on their own with a logistic law. And we assume this rho is very small. So the major contribution comes from the resting nuclei, which then mature into bulk cells. So that's that. And then the moving nuclei. So then the moving nuclei, they move along the microtubes. So we use another transport process for this, where we know the probability to choose a new direction is given by the microtubes which are present. So this M here is the normalized microtube directional distribution. And we use this for what I earlier called T of VV prime. This is now M at TXV. In the framework I just showed you in an earlier slide. So that's the same setup, the same idea, but with a different T. So T is now little m, and this comes there. Nuclei are produced by cell division from existing nuclei, and they mature into resting nuclei and then into bulk cells. Okay, and then the last equation is for the resting nuclei R. So they then they come from moving nuclei in the microtubes, and then they mature to become bulk cells with the rate gamma. Okay, so far so complicated. So then putting it all together, we get these 5 equations. And yeah, they don't look too bad, but also not too friendly maybe. They have 2 transport equation terms. The other 3 are ODEs, which is a little bit better to deal with. Okay, so what do I do here? Oh yeah. So then next we look again at the videos of Oswald. So these videos I've just shown you, they're more in their paper. And we can estimate a whole bunch of these parameters. So we just look at videos, we can see how fast nuclei grow, we can see how fast microtubes grow, and we get all these rates here which appear in the model. So here they are listed. And okay, now back to the model. So then the first idea, if you have a complicated PDE, is to look at the kinetic part, and the kinetic part is everything without space. So you throw away all the space terms. This is a spatial term, this is a spatial term, and these are spatial terms. And you just focus on the kinetic part, which is all the reactions that happen. So which we do here. There we go. So these are all the terms without space. And now it's a 5-dimensional ODE, so we can do all kind of stuff. We can look for steady states, we can look for their stability, we can do a little bit of numerics. And I do that. So here is the steady states. We have disease-free steady states where the cancer is this entry here is 0. We still can have microtubes, which just sit there and do nothing. But the cancer density is 0. Or we have disease steady states where the cancer density is at carrying capacity, K. Again, we have microtubes and nothing else. Let's look at a simulation. Simulation is here. So time in hours on this scale, and the density of the 5 compartments are here. And what you see is, what do we see? Well, let's look at the black one first. The black is the tumor bulk. And so this grows very quickly here in this simulation. But you see the growth is initiated here by the red and blue at the beginning. And the red are the tips, and the blue are the tumor microtubes. So you see the first thing happens is the tips and the microtubes, and then they lay down essentially the path for the black, which is the tumor bulk. The moving nuclei, the resting nuclei are these ones here at the bottom, and they, of course, participate in this growth to make it happen. Yeah. But important is that the leading or the key mechanism here is at the front, which is the tips and the microtubes. We can do a little treatment simulation. So here at time 3,500, we just remove all the black. We remove all the tumor cells, but we keep everything else. And you see the regrowth is instantaneous. It's very quick. And the reason is because we kept the microtubes in the system. And this, I think, is already an explanation why treatment of brain cancer is so difficult. Because you can see tumor cells, you can take out tumor cells, but you will not be able to see microtubes in the MRI scan. And they're like super small. And if you leave them behind, then from there, you might get a new tumor growing. Okay. Here is a full model simulation. So Nadia Loy, one of my collaborators, she wrote a program for this 5-dimensional PDE system. And you get wonderful invasion fronts. And again, if you look here at the front is led by blue and red, the microtube dynamics, and the black is following that movement. Okay. Now, this model is still too complicated to be used. So this 1-dimensional simulation is already very costly for a transport equation, and it takes several days to run. I think this simulation took actually 2 weeks to run. So this is not very useful. And it's 1-dimensional, and a tumor is 3-dimensional. So what we need is we need to reduce the model to something simpler. And that's what we do here. So now here I have a scale of 1, 2, 3, 4, 5, 6 models, which go from complicated to simple. And this here, the full model, this is the 5 equations I've just shown you. And down here, as we will see, is actually the Swanson model, which I started with. Okay, so then I have a series of simplifying assumptions, A1, A2, A3, A4, A5, A6, which gets me actually down to a much simpler model, essentially the first model which was ever used for this kind of glioma modeling, the model by Swanson. And not only this, so we also get other models which we know already. For example, the Go or Grow is the model here by Pham and Hatzekiro, shows up in this, and the anisotropic model shows up here in this light green. Okay, so all the 3 models I've shown you initially show up as special cases if I go to a sequence of simplifying assumptions. Now, this is pretty cool. So let's see how this works. So the first assumption is, so from the purpose of my course, it is important to go through these assumptions because this is very typical analysis stuff or modeling stuff, and shows you how to deal with complicated systems. So I assume the resting nuclei are in quasi-equilibrium. This means that the process of nuclear resting and developing is kind of fast, and the microtubes and the tips are in quasi-equilibrium as well. Quasi-equilibrium also means that you set the time derivatives to be 0. So here's the model again, and I set the time derivative for the m equation 0, for the n equation 0, and for the r equation equal to 0. This means quasi-equilibrium. It is an approximation, okay, but maybe in some situations, in particular, if these reactions are fast, these Brown reactions are fast and the other ones are slow, then you can do that. Now these become algebraic equations, right? You can solve this for sigma p, this kappa and m, and it shows up here again, and it shows up here again. So you can simplify these olive-colored equations quite a bit, and then replace maybe the r here with kappa and m, and then kappa and m with a b and with a p, and so on. Right, you replace it with a p. And then you get a system between p and b and nothing else. And so this is this system here. So I call this a tips bulk model. So the first equation then is still for the tips, and the second equation is for the bulk, and that's what you get. The p bar here, the p bar is the integrated version because it depends on velocity, txv dv. And if you integrate over all velocity, then I call this p bar, because the bulk equation does not depend on velocity. Okay, so this equation is still too complicated. We are not happy. We want to rescale it using the parabolic scaling. Parabolic scaling, you assume you have a fast time, tau is epsilon squared t, and space, a macroscopic space, xi is epsilon x, where epsilon is a small parameter. And we also assume the reaction terms are low order, so they're of epsilon, order epsilon square. And if you do this, then this transport equation term here simplifies. And maybe before I show you what it simplifies to, I do it as an example, because this is something I like to teach. Okay, yeah, I do this right here. So example, I do this for the Pearson walk, which I mentioned just earlier. So the transition probability here is 1 over v. Okay. So let me walk you through this method of parabolic scaling for the Pearson walk before I continue then with my model here. All right. Just, yeah, I want to write it in this form. So I write down the Pearson walk again. V times gradient P equals minus mu P plus mu divided by V integral P Tx V prime dV prime. And I assume that the space of velocity is a speed times any direction. Sn minus 1, same as before, we have a unit sphere with a radius sp. And this integral is on capital V. And so then the size of capital V shows up there. All right. So now we do the time scale. So tau is epsilon squared t. And xi is epsilon x. And then we do a perturbation expansion. Of the form P of tau and xi and V. Yeah, it's the term P0, which depends on the same variables, plus a lower order term epsilon P1, tau xi V, plus epsilon square P2. So this is very standard method. Plus epsilon cubed. Okay, doesn't want to write there, so make dots. So you can go as high as you want, and we only need to go to epsilon square. So this is the assumption. Oh, I need space. Space, space, space. And I assume that all the mass is contained in P0. So I assume that all the integrals over Pj of tau Cv dv is 0 for j larger or equal 1. Okay, from the higher order terms, I assume that they integrate to 0 if integrated over velocity space. So the mass is in P0, and P1, P2, P3 are perturbations from P0, which have the average equal to 0. Okay, so what do you do now? First of all, we rescale the equation using the new time and spatial variables. And if you do this, if you translate d by dt, you get a factor epsilon square. And if you do the spatial derivative, which is here, nabla, you get an epsilon. So what we get is rescaled. We get epsilon square p tau plus epsilon v times gradient p equals minus mu p plus mu divided by v integral p of t tau c v dv, or let's call this prime v. Okay, so here we get epsilons in there. So now you take this expansion, the perturbation expansion, and plug it into this equation. Okay, so if you do this in the first one here, for example, you get epsilon square p0 tau plus epsilon cubed p1 tau plus epsilon to the 4 p2 tau, etc. And you sub it in here, and you sub it in here, and you sub it in here. So if you really write this out, you get maybe 5 lines of terms. But I don't do this. I don't do this. I just keep it in my mind. And I compare orders of epsilon. Compare orders of epsilon. So the lowest order is epsilon to the 0. Come on. Yeah, epsilon to the 0. So let's look and see which of these terms, if I sub in this perturbation expansion into my equation, which of these terms has no epsilon whatsoever? And now this is a real question to the audience. So which terms has no epsilon? On the left-hand side, let's start with the left-hand side. Who can do this in their heads? Sumaira? Put you on the spot. So which term would have no epsilon whatsoever on the left-hand side?
They all have epsilon.
They don't have. Thank you very much, right? We multiply everything with an epsilon square or with an epsilon. So here's a big 0. Thank you. But on the right-hand side, what do we get if we sub in this expansion? Yeah, the 0-order term is this one, right? P0. All the other terms have epsilons. So then if we sub in P0 into our integral and so on, we get one of these possible terms. So minus mu P0 plus mu over V integral over V P0 of tau C V dV or V prime dV prime. So this is the 0-order equation. Okay. So we want to solve this now. This is an equation essentially for P0, right? We can write this to be P0, and now I write out all the dependencies. We move it to the other side, we divide by mu, so the mu goes away, and this is 1 over V integral V P0 of tau C V prime dV prime. Nice. So this looks like an integral equation for P0, but actually it is simpler than that, because the right-hand side here, you integrate over velocity. So whatever comes out is not depending on velocity. So it does not, come on. Yeah. Does not depend on V. But here we have a function that depends on V. And this cannot be the case. Okay? So this shows us that P0 is actually independent of V. Need a new page. Give me a new page. So then from this we follow, where's my red? Come on. That P0 of tau and C is independent of velocity V. Very important. Now, if you assume P0 is independent of V, we can look at this equation again. So let's look at star again. Then we have P0 of tau and C is now 1 over V integral of P0 tau and C dV prime. Now it doesn't depend on V prime, so we take it out of the integration and we get 1 over V P0 tau C. And the integral gives us just the size of V. And so the two sizes of V cancel, and we get P0 of tau and C. So this then automatically satisfies equation star, which was our leading order terms here. So then that's it. So P0 depends on tau and C, but not on velocity. Okay, so let's move on to the next level. There's still something in the way? Yeah, you get it? Yeah, okay, thank you. All right, so then, oh yeah, next level, epsilon 1. So now we are experts, we all know what to do. We take this expansion, we put it into this equation, and now we look for all terms which have exactly 1 epsilon and not more than this. So who wants to give me some? Any volunteers? Do it. Come on. No? Right, so here's an epsilon square. Whatever I multiply, this is too much. Here's an epsilon. So if it multiplies P0, I get exactly 1 epsilon. If it multiplies P1, I get epsilon square, which is too many. And on the right-hand side, if I sub in P1, P1 carries 1 order of epsilon. So what I get is this. I have V times gradient P0 is a minus mu P1 plus mu over v integral p1 of tau c v dv prime. So these are the order epsilon 1 terms in the system. Earlier I said that p1 integrates to 0. Where did I do this? Here. Here I say the integral of the pj's, if j is larger or equal to 1, is 0. So this happens then to this term. This is 0. And I like to solve this for p1. Okay, I know p0 already, so I want to solve this for p1. So then p1 is just minus 1 over mu, v times gradient p0. So if I know p0, I know p1, perfect. Okay? Okay, so then we do one more, epsilon square. So if I look for the epsilon square terms, now this is the first time the time derivative plays into this. So then we get p0 tau derivative plus v times gradient p1 is minus mu p2 plus mu divided by v integral over v p of tau c v prime dv prime. And this is p2. So second order in epsilon. Okay. Now we could try to solve it for p2, but I do actually a simpler step. I just integrate this over velocity space. Here we have it again. So we integrate over velocity space. So this capital V space. So what happens? Well, remember, p0 is independent of velocity. If I integrate this on velocity space, I just get the size of the velocity space, p0 tau. The next term, though, has a v in there, right? V times gradient p1. So I keep it as an integral. So integral v times nabla. And then p1 is in my box right here, minus 1 over mu, v times nabla p0. And all this dv, okay? And on the right-hand side, we get minus mu integral over v p2 of tau c v dv plus, and then here we get a double integral. We get mu divided by v integral over v p2 of tau c v prime dv prime dv. Do I have space? No, no space. dv underneath is a double integral. Okay, let's look at the double integral thing here. The integrand depends on v prime. The outside integral integrates on v. So we can do that first, and we get the size of v. So then what happens here is minus mu integral p2 tau cv dv plus mu integral v p2 tau c v prime dv prime. So this is what I keep. The 1 over size of v will be cancelled with the other integral there. Okay, what is this? Can I simplify this? I can maybe write it nicer. This one here is not very nice. So this is a dv. Anybody, can I simplify this? It's 0. I want to hear 0. Why is it 0? Because I just renamed the integration variable, right? Here I integrate on v, there I integrate on v prime. It's actually the same. Actually the same. So this is 0. Nice. Okay. Nice. So we get a lot here. Oh, that's cool. So all the right-hand side is 0. So let's focus on the left. And I divide by the size of v. And this integral term here has a minus sign. So I can move it to the other side of the equation. And I get 1 over mu and size of v. And then I get this complicated integral V times nabla. And then I get another V times nabla. Let's put this in brackets. P0 dV. Okay, now we do, so now we have to do some higher, what is this, multivariable analysis. So like third-year analysis course using divergence and gradient and vector value things to write this in a more pretty form. So I probably need more space. Okay. So this P0 does not depend on velocity. So I can take it out of the integration. But it depends on space, which means the derivatives here, they act on P0, and this acts on P0. So if I take it out of the integration, I need to be sure I still obey the differentiation process happening. How do I want to do this now? So I can write it in this form, 1 over mu v, yeah. And it turns out that this will be our colon derivative later. Yeah, okay, I have to do it component-wise. All right, so I integral v sum over I and j. So the first one is a product of vi and d by dxi. And the other one is a vj d by dxj. These are the vector products. And all this integrated on v and then p0 of tau and c. So I can still take out P0 from this integration thing. That is fine. And now I switch the integration and the sum. So then I have 1 over mu v sum I and j equals 1 to n. Yeah, let's do it step by step. So vi d by dxi, vj d by dxj, dv, p0 of tau and c. So let me drag you through this at least once in your life. Life will be nicer once we have done this. So then I take out the derivatives to the left. Then I have sum I and j, d by dxi, d by dxj, of an integral of vi, vj, dv, p0 of tau and c. And what this is already, this is actually a tensor, right? You can write this to be the diffusion tensor. It depends on two coordinates, vi, vj, and you integrate this over velocity space. So whatever you get, it will be a matrix. And then these two derivatives we can identify, as we did earlier, as a contraction of two tensors. It's another way to say it. It's a contraction of two tensors. So this has already the form I indicated earlier in the anisotropic case. But we can do better. We can show, and maybe I skip the details of this one, that the integral of v, vi, vj, dv is actually a coefficient times the identity matrix. So d times 1, 1. Or actually, it's the diagonal matrix with all the d's in the diagonal. Also a case I mentioned earlier. Okay. So then, the colon notation, nabla, nabla, colon d, simplifies to be a Laplacian. And then this becomes 1 over mu v d time Laplace of p0 of tau and c. Oh, wow. Lots of work. My goodness me. So yeah, this is, so what did we do? I need just a little bit more on one page. Something equals P0, now Laplace P0, but what, where did we start? We started here with the time derivative. So we get P0 tau equals d divided by mu and V Laplace P0. And this is just the heat equation or the diffusion equation. This is a standard diffusion equation. Okay, so this is how the parabolic limit works. So we started with the transport equation. We did these perturbation expansion. We used some tricks in higher dimensional calculus and integration, and then we get this diffusion equation popping out. Wow, and I used lots of time to do this. So now we are ready to appreciate what's happening in our microtube model. So P0 is a leading order term. If I integrate it on velocity space, I call this U. And then I do get this diffusion term. I derived it for the Pearson walk, but you can imagine this can be generalized. And then you get this nabla colon diffusion tensor in there. And we get an equation between U and B. And the diffusion tensor is a second moment of an equilibrium distribution psi of V. So it's really a generalization of the Pearson walk, which I just did by hand. Okay. In the isotropic case, so for example, for the Pearson walk, so here we can now write Pearson. This diffusion tensor becomes the identity matrix, and we get a scalar thing. So we just get the d Laplace u, as I've shown you earlier. Nice. So this comes together really nicely. Okay. Now this is the same. So this model now is of go or grow type. We have a first equation where we have diffusion, and we have no diffusion in the other one. And we have like a logistic growth term in the second equation, which is missing. Well, no, we have a logistic term here as well. So it's a go or growth type. It's not exactly the go or grow model, but it is very similar. We have a moving compartment and a non-moving compartment, which reproduces. And so these models have been studied by several people, like listed here. And then a final step is we can assume that the tips and the bulk are related. In fact, if we look at the images, we can see that the bulk cells have 3 or 4 microtubes. So the relation is about 4. And if we use this in our equation, then we get an equation for B alone for the bulk, either in the anisotropic case or in the isotropic case. So here it's the anisotropic case. And that's the model which was used by myself with the Painter, Swan, Sorolescu, Engber, etc. Or the isotropic case here, which is used by Swanson. Okay, too quick. Here we go. And that's essentially the Swanson model. Now, this Swanson model you can simplify. You can call the coefficients d hat and mu hat and k hat, and it becomes the Fisher KPP equation, which is also very well known. And the d hat and mu hat and k hat we can identify as here, giving the original parameters. Yeah, this is nice. So if you know the parameters of the microtube dynamics here, like we did from the Oswald paper, we can actually estimate the carrying capacity, the growth rate mu hat, and the diffusion coefficient d hat. That's wonderful. Okay. Yeah, and that's a model used by Swanson and her group quite a lot. And back to here. Okay. So now we have a series of assumptions which are listed here, A1 to A6, which very clearly give us the previous existing models, the anisotropic one, the go or grow one, the PI model one, which means we can now scrutinize the biology and say, okay, do I have all these assumptions in place? If yes, I use the simplest model maybe right here. If A6 maybe is missing, then I have to go to the go or grow case, or if F5 is missing, I have to go to the anisotropic case, etc. So you can relate this directly to the biology, and you know what assumptions are underlying these models which have been used before. And I think this is really cool. Okay. So I use so much time, actually, just invite questions. Are there any questions for this more theoretical part? If not, then I just want to, I skip the invasion speeds. And Alexandra, I skip your lesion studies. This one. And I just show you how this is used in real cancer patients. I make this slides available online anyway, so you can look at it back. But if I do everything, I will be over time, and I don't go over time. So let's look at brain tumor modeling. So now we have this scheme of all the different models. And I want to ask the question, how actually has this been used in the modeling of brain tumors? And let's start with the simplest case with the Swanson model. So this has been modeled actually, used actually a lot. I would say hundreds or maybe 200 of patients or even more. And typical simulations look like this. So here on the left, you see the cancer of a patient at diagnosis. And on the right, you see the cancer at the patient's death. And in black outline is the cancer size. And you see overlaid is a solution of the Swanson model in colors of green and blue. And this shows you how far actually the tumor would have extended beyond the visible region. And this is actually quite far. This is amazingly far. So essentially it has affected half of the left hemisphere quite drastically. Okay. And yeah, and then at the patient's death, of course, everything has grown quite a bit. So this is typical simulations using the Swanson model. Now for the Go or Grow model, there's a paper by Sort where this has been applied to real data. And I'll show you this here. So here are a time course as we go from left to right. And this compartment here is the growing compartment. And this compartment is the Go. And actually they include a necrotic core, which I didn't have in my models. Necrotic core just means there's no more oxygen. And so so the cancer cells die in the very middle of the tumor. Okay, but the Go is clearly leading the invasion, and the Grow is following this invasion, and this can be really seen. However, this here is not a sick patient. This is a healthy person. A healthy person's brain, maybe it's Sort's brain actually, I'm not quite sure, with a just numerically implanted tumor. But this patient was never sick. Okay. And then, yeah, so we looked at the anisotropic case where we now use the diffusion tensor formulation. And then we get images like this. So here we compare, we did this for 10 patients. Here I show patient 8, where we compare the anisotropic model and the model by Swanson, so the simpler model. And what you see in these pictures is the detected tumor is the black outline, and the white line is our predicted tumor in the same situation using our models. And you see on the left, the white and the black, they overlay very nicely. In the Swanson case, they also overlap very nicely. So this is nice. In colors from red to blue, you see the level of anisotropy. So blue means it is very homogeneous tissue, and red means these are white matter fibers. So this one would be white matter, where the diffusion becomes really anisotropic. And in this case, it seems the anisotropy doesn't matter at all. So both models are really good, and they show the real tumor really nicely. Patient 7 here, there's a little bit difference. If you look here in this region, the Swanson model in white predicts growth here to the right, which our model does not. So there is some improvement in the fitting of the tumor size if we use the anisotropy, but it's maybe not too bad, too drastic. And then I'll show you one more, which is the patient number 9, which has a quite irregular shape. If you can see the black shape. So there's lots of outgrowth here on top, which the Swanson model is missing completely. Our model here does a little bit better, but it's also not perfect. It doesn't show the outgrowth completely well. So it is an improvement, I think, but it is also not the end of the story. Yeah, so for example, in this region here, Swanson model is actually better than ours. Yeah, so that's how it is. Okay. So then looking back at this scheme again, so the bulk isotropic Swanson model has been maybe used for hundreds of patients. The anisotropic model has been used for 10 patients. And then the go or grow model has been used for one healthy person. You cannot say patient because it's not a patient, it's a healthy person. And that's it, right? So none of the higher level models here have been used in any kind of clinical study or for any of the brain images and so on. So there's still lots of work to be done. I think the scheme with the assumptions is really useful because, as I said, you can scrutinize the assumptions. It tells you on which level you should be modeling. But these higher level models have never been used for any real data. And that's something we should maybe aim for, maybe do. Okay. Yeah, so let me conclude. So the tumor microtube driven, here's an N missing. Glioma model can be reduced to the previous models in special cases, which is nice. It opens a door for more targeted patient treatments. There are mathematically interesting questions, right? I've shown you this derivation of a transport equation, parabolic limit. Really cool stuff, I find. And the tumor microtube-induced anisotropy is not a dominating factor in wound healing assay. Okay, so I didn't talk about this today, but this is a result for Alexandra. So maybe if Alexandra wants to give a talk here in my lecture or so, we can talk about this. But yeah, but I think this is a good taste of where the research stands in the spatial spread of glioma modeling, and there's still lots of work which can be done. All right, so I finish here for today. Any questions? Yeah, thank you. Questions for my multiple audience here? All good? Yeah. Yeah, thanks very much. So then on Thursday, it's again me. I will talk about the oncolytic viral therapy. And then a week later, it will be Tom Yankilov. And I think he comes back to the glioma modeling. So he will probably mention a few things which I mentioned as well today. Thank you very much.